Soil Technology, Session 1. Understanding soil. What forms the soil? Where does soil originate? Soil is a result of the breakdown and decomposition of magma, volcanic rock, in the molten state, which then solidifies. All soil is a result of the breakdown of magma, because that's where it originated. Okay. So it does all come from volcanic rock in various stages of decomposition and mechanical breakdown. It is made up of sedimentary rock, volcanic rock, or metamorphosed rock. Metamorphosed rock comes from the reheating of soil. When a volcanic dike extrudes into the soil in its molten state, the heat that is generated is so great that the surrounding soil actually fuses back into rock, and that is called metamorphosed rock. Sedimentary rock is formed by the pressure of overburden exerted under high conditions of pressure to cause the rock to almost fuse. Not fuse in the sense of heat. Certain amount of heat may be produced, but it is primarily pressure, which then causes them to fuse together, and that's known as sedimentary rock. General idea of the breakdown is illustrated by this sketch. You've got the magma, which breaks down through weathering, decomposition into soil. Now, that soil can be reheated, which then forms rock, metamorphosed, which is metamorphosed rock, or under pressure it is formed sedimentary rock. There are other forms of soil which are known as pedogenic soils, where water actually with metallic ions dissolved eventually evaporates, leaving these metallic ions to fuse into the soil particles and cause them to form a rock. These are various types. The one most common is what we call ferricrete, where the actual ion is ferric ion or ion. It's an iron ion. Okay. Then you also get rock as a form of the calcium presence in water, which then fuses, forming a calcrete, which is calcium oxide, or calcrete. When silica is the dominant ion, you get a silcrete. What is the makeup of soil? Soil is composed of solids and voids. The solids have size, different sizes. They are of different shape. They are a different mineral content. And of course, they have a different form of mass. The voids, these now, on the other hand, are the open spaces and may contain air, ore, and water. And that makes up soil. Here are diagrams, diagrammatic, showing various properties of soil. The degree of saturation, S is the symbol, is the volume of the water over the volume of the voids. Now, the void or solids ratio, which sometimes could be referred to as the degree of interlock of the particles, like this, are made up of the symbol for the degree and for the solids ratio is L, and that is the volume of the solids over the total volume. So it is that fraction of the total volume which is actually made up of solids. Notice that these are all ratios that I am talking about. They have no dimension. Now, the voids ratio, which is got the symbol E, is the volume of the voids, or the air open spaces, and over the solids. It's the volume of the voids over the volume of the solids. And that ratio is known as the voids ratio. The voids ratio, incidentally, and the solids ratio are direct measures of strength. The greater the solids ratio, the greater the strength. But the voids ratio is just the opposite. The smaller the voids ratio, the stronger the material. The best ratio for strength is either the solids ratio or the degree of interlock. That is in fact what we do when we compact a material. We push the material together so as to reduce the voids and to give the solids, the whole of the particle, more solid and less voids. And that is what makes up strength. Strength actually is formed by the friction between the particles and the degree of interlock that we get. So that the solids ratio and the voids ratio are direct measures of strength. Density in itself is not a direct measure of strength. Although we know that when we get a higher density in a soil by compacting it, we will get a higher strength. But we've got to relate that to some strength which we've prepared by doing tests in the laboratory. And we relate that in the field to that which we've got in the laboratory to know whether it's the right strength. I would like to see in future the use of these degree of saturation, the degree of interlock, or the solids ratio or the voids ratio as direct measures of strength without having to do anything else. If a material has got a high degree or a high degree of interlock, or it has a high solids ratio or a low voids ratio, we know straight away the material has got a good strength. Now, N is the porosity. It is the ratio of the voids to the total. Then we've got the water ratio. Moisture content as a percent of the mass of the soil is not a true relationship of soil and water. The right relationship is the water ratio, which is the volume of the water over the volume of the solids. Normally, we express water as a percent of the solids mass. Unfortunately, the same volume of water, when expressed against a material that has got a high mass, because the material's relative density is high, or specific gravity is high, you're going to have a high moisture content. But that same moisture content will not be the same in percent if the material is of a lighter type of material or lighter particles. That makes the percentage not a reliable measure. Whereas the voids, the water ratio, is a direct measure of the extent to which the water has actually reduced the strength of the soil. Because water acts as a lubricant and reduces the internal friction between the particles. Now we've got the relative density. All particles are not always of the same density. I'm speaking about the particles now, not the soil. You may have a heavy particle or a light particle. If the material, just like a stone and an equal amount of volume of wood, the wood would be lighter than the stone. But you get now some heavy stones and you also get light stones. They're compared to the same volume of water, that material is now, the relative density of the material is the comparison of the volume, the mass of the soil, or particle rather, to that of the actual volume of water. When it comes to particle size, we define soil to a very large extent by the dominant sizes within that soil. A soil may be fine-grained or it may be coarse-grained. It may be a gravel or it may be a sand. So the size of the particles making up the soil, even although they may be of different sizes, the dominant one has a tendency to give us an indication of how that material will behave when we use it in a road. The largest size are boulders. Then we've got cobbles, and then from that we go down to gravel, and below that is the sand, and below the sand we get silt, and then the finest particles right down the bottom is the clay. Now we've got soil is not like a solid mass. Soil can have movement within itself. If it is pushed, the volume within that and the particles within that soil mass actually move relative to each other. And that's movement that can take place within the soil. Here is an example now of compaction, where we've got particles that are relatively loosely compacted or loosely related to each other. If we apply an external force, we push those particles together and we get them into a closer knit state. Now, if we have to move the particles, they are going to be in contact with each other, because it is the particles in contact with each other that actually make the soil stable. There is no strength if the particles are floating in air. They must contact each other. And in order to push those particles over themselves to get to a stated degree of density, those particles, we must overcome the friction between those particles. And this sketch shows if we push a particle over a plate or another surface, there is something that is going to resist that movement. And that resistance is known as friction. We have this then, that resistance or frictional resistance, which if it equals the applied force, then movement will stop, because the applied force is not sufficient to overcome the friction. Or in other words, the friction now equals the applied force. And that friction results in what we call the compression strength of that material. It's the amount of resistance which that material offers to further densification. Incidentally, some of these symbols I've introduced myself in order to be able to classify the difference between various strengths and various soil conditions, which have not generally been defined in the term of geomechanics. The CBR, which we can shorten by just using the symbol B, is the actual strength of the material, which is the strength resisting breakdown of interlock. It is, in other words, just the opposite strength to that of resisting compression. This one actually resists dilation, and that resistance now is known as the CBR, or it is a ratio. CBR is a ratio again, but it is a form of measure of the strength of a material, which is internationally known as CBR, California Bearing Ratio. Here's a sketch showing that when particles move over across each other, there is a movement and an increase in volume. Compression is a decrease in volume, whereas failure is an an increase in volume, and a dilation takes place. And the dilation is the degree of expansion that must take place before the particles actually move over each other. We can equate that to a breakdown of a man pushing a large boulder up a hill. When the boulder has gone to the top of the hill and starts rolling down, it's easy to break down. And you get a curve there like that and that is the initial strength of the material, which is the strength or resistance to break down, and this one is the rolling resistance. That one is the dislocation resistance, whereas this one now over here is the rolling resistance. When a material is stockpiled, it forms a certain slope, and that slope is formed by the rolling resistance of the material. When we cut a bank that has already been compacted, it stands up vertically, provided it is not too high. And that now is the initial strength, which is we would call the strength resisting movement. Then that is now the lot.